So the next thing is the contexts. And okay, here's a question. Would anyone can imagine how the context would change in this version? Like, what would be the difference? It's quite very straightforward, trivial.
So the keys in the context would also be types.
Yes, yeah. So now the types traveling and collapsed. So all we do is we just extend with some arbitrary variable. Could be term of some type, or could be type of star. Context validation, only a trivial change there. Essentially, what you need to do is, if you have a valid context and you have something which you can check that it's a type, then you can add a variable of that type. Fairly self-explanatory. And okay, here we have the exciting part of type inference. Okay, if at any point I'm not clear with this, then please ask me to clarify. So first we have our inconsistent star has type star. And okay, so a few of you said that you're not familiar with this idea. So so essentially, the research on dependent types came from the desire to formalize mathematics. And there is a correspondence between dependent types and quantifiers in predicate logic. So the idea was to be able to encode predicates about mathematical statements. And what happens is that, and then as programmers, what we want to do is we want to use those predicates to enforce certain invariants about the program. Like, the proposition, the types connection, it says that if your type, okay, so the question is your type inhabited? And what that means is you're able to construct arbitrary type definitions using your type language. And the question is, will this type definition have some term within it? Or is it just gibberish? Like let's say if you say, for random gibberish example, if you say 3 is a type, then obviously there's nothing going to be within 3. Well, it's not going to type check, but if it did, it doesn't have any terms. Or you could make, if we use some, a little bit of a digression into how an existing dependent type language would do it, then you have type void in Agda or Idris, whatever, which has no inhabitants. So there's no terms of type void. In contrast, there's also type unit, which has 1 inhabitant. There's type bool, which has 2 inhabitants, true or false, etc. So the reason the inhabitant question matters is that once you have a few more pieces within your dependent type theory, then you are able to construct logical formulas. And the question is your formula correct? That question gets translated into, does your type have any terms inhabiting it? Does that make sense?
Yeah, so we don't want to allow empty types because otherwise we are able to write a false proposition.
Well, you allow empty types, you just can't do much with them. So you could, you could create a type void, and so once we have the REFL constructor, so we're gonna tomorrow get the REFL constructor, which is essentially a question of are 2 types equal? And most types are not equal, but if you have a proof that they are, then you are able to kind of convert one from the other, for example. So, for example, but you can use REFL for like asking some weird things, like is I don't know, integer equal to bool. Technically, that's a valid type, REFL int bool, but it's going to have 0 inhabitants. So in this case, however, the problem is that star to star, it kind of breaks that. So it's not that we don't allow empty types, it's the opposite. When you have star to star, all of your types have an inhabitant. It's the same as proving false in logic. If you're proving something which doesn't exist, you're always able to fill your type, which we don't want, but since this is not a logic conference, and this is just an implementation of the Venn types talk, it's a good starting point. But how this is resolved, if you were to go and build other languages after this, is that we have a hierarchy of type universes. So you would have, let's say, naturals have type, and then, or star, and then, or star 0, and then star 0 has type star 1, and star 1 has type star 2, and you can just go on forever. And when you have the universe hierarchy, then you can regain consistency. But it would be, a little bit too much to implement at this point. So yeah, that's where we got star star. So some background there. Let's see what's the other thing. So okay, here's an interesting and subtle change that's happened. Previously, we would have seen expression has type T, and so these are different now, as you can see. So what it means is that because types can contain computation, we might give, you might supply your term with an annotation, but it might evaluate to something different, like a simplified form. Like if your type has a function body, like for example, like here, for example, you have x of type, and we give it a value of not. So then this becomes simplified, and it becomes this thing reduces to y of type natural. So it has simplification in the type body. So essentially how we go around that is we say that if our, let's see, so what first we do is we check that this is an actual type here. So it has, it's a star versus, you say a nonsense, again, nonsense statement like expression of type 3. So once you've checked that P is an actual type rather than a term, then you evaluate it. You simplify whatever needs to be simplified, and you get some other type which we denote as T. And then you go back to your expression, and you check that your expression actually matches type checks under type T. And if it does, then we can infer that your expression actually has type T, which is, again, T is a simplified version of P.
Is there a way to for vice versa, like E type tau enforced type rho?
Okay, so what would that mean? But then E type tau. But then what? So then, if you mean if we call this constant, we don't rename. So, but then because we're.
No, everything about the line is the same.
Yeah.
Can we infer that the bottom line is true when we swap tau and rho? Can we infer the type of E colon tau is rho?
Right, but what? So rho is something we're supplying, and then tau is something we're inferring. Does that make sense? So then. Oh, so you want to infer the type annotation, like? No?
No, but like the annotation of the top of the bar, it shows
Yeah.
down arrow for both.
Yeah.
Oh no, it's not E.
Or,
it's P as a type.
yes. Yeah, we're checking that it's just a type, and then we simplified, and then we check that the actual expression matches the simplified type. So this is like the, imagine it as a complex computation, and we just simplified it. Yeah, but no, it's a good question of how you're thinking, because a lot of these, like, it's good to try and vary them and then see what happens. Yeah, I guess this is we've introduced a new rule here, and essentially the question is, what does it mean? How can we infer that the product space is an actual valid type? To do so, we first we need to check that the input row is some kind of type, and then we're checking that, again, we evaluate it to a simplified version, and then we check that, so basically the tricky bit is that x can be found in row dash. So yeah, we're simplifying the input, and we are checking that a context extended with x of the evaluated type. Within this context, we can derive that row dash is a type, because this is the type signature. So it needs to take some type in and put some type out.
Why is it important to add x to the context?
Because we are, remember this is mimicking how the same case with the simplified version, where we were we had lambda x to expression, and so because lambda x can be anything, essentially we're kind of assuming it in a context, because you're how do I say this? You're extending your context with this kind of, like, imagine this as a hypothetical potential variable, because you can't create a function referring to a non-existing argument. It needs to have some kind of name. So essentially you're just extending it here. You're just assuming that there is some kind of thing which is x of type t. And if there is x of type t, it just allows you to kind of do the inference for the function space. Do you remember the the version in the simply type case? You see them side by side. Wait, type inference, type checking. Yeah, if you look at the lem rule, remember how here we also, in order to check this part, we remove the lambda, and then we check the body, and then, but to check the body, we need to kind of extend the context with this x of type t. So here is the same thing. It's let's see. Except it's happening at type level. Right, and there's also, and again, a very similar case with the lambda modification, actually. In order to check the body, so we have, in some context, lambda x to expression, and we can check that it's a valid dependent function space. So we do it by extending the context and checking that the inner expression has the type tau. And likewise, yeah, the check rule, which is exactly the same as last time. Right, and one more thing here is the notion of equality. So, and this is kind of like a little bit of a hint of things getting, where things go crazy in type theory. Because different type systems have a different notion of what it means for two types to be equal. So I kind of glossed over it with the INN rule. So essentially, you know, we're kind of like here we're assuming that, you know, P and T are the same thing, and but what does it mean that they're the same? And we're using this classical notion of equality, which is essentially, you know, 2 plus 1 is the same as 3. They're not syntactically equivalent, but they reduce to the same normal form. And so with these kinds of rewriting systems, intentional equality eventually says that if two things reduce to the same normal form, then they are the same thing. And this is why type theorists spend a lot of time proving that everything terminates. Because if everything terminates, it means that everything reduces to something. And then you just have to wait for it to reduce, and then you check if that reduction is equal to whatever you want to compare it to. So here we have the conversion rule we're using here, which is the equality check. So we know that if we have an expression of type P, and P includes some computation, and this computation reduces to P dash, then it's the same as saying that E has type P dash.
So it's another notion of reduces different from Zans error.
Oh, okay, so no, this would be, it's more like, not so much judgment so much as we're kind of, in our type system, the only time we really care about it, checking that two types are equal is in this case. However, for example, there are type systems like you have here where you go from inference to checking, and someone I think asked in the first lecture is what happens if you have the reverse? What happens if you start with a check? Can you get an inference from it somehow? Like it's not symmetrical, and so what we could do is we could, using various equality rules, we could add more rules to the system, which would allow you to kind of capture, inch closer towards a symmetric case, if that makes sense. So you're able to extend the amount of expressions which type check, if that makes sense. So, okay. How do I say it? So it's possible, okay, it's possible that
What is the definition of equals beta in alpha?
oh, okay, cool. So this is just bait reduction. So it means that there's some kind of lambda abstraction happening and is being applied to, and you keep simplifying it until it goes to RW. So again, this is the difference between something like a system with Haskell, where all of your types are static. You create a type and it's just there. It doesn't change. Well, but whereas here, your types have computation. They take some input and they do something, and because they call them type families. So in a technical sense, when you have a type family of, like, let's use vectors as an example. You have for all n, for all n to for all type not, and for all a of type, we have vector and a, right? You guys familiar with the vector type? It's like a list. So a list would be, it takes in an A and returns a list of A's. A vector, it takes also a natural number which says how many elements are in this list. And they call them type families because you can imagine it as something, it's not a type yet, but it returns a type. So it takes in some values and then creates a type. So for example, vector 5 bool, you can imagine it as an evaluated type. And vector NA is just a function which waits for 2 arguments to give you a type.
So can you give an example when equals beta is different from arrow down?
Equals beta difference to arrow down? Oh, I see. Well, it's not so. You wouldn't. It's not that it would be different, but it's more like your algorithm for arrow down or arrow up might be using equality.
Double arrow down.
Double arrow down. Oh, evaluates. Oh, I see. Oh, no. So yeah, you can see it as being equivalent. Yeah. Yeah.
Question about beta, actually, the conversion. So intuitively, that seems like you have something p or rho or whatever, and you can convert that to p tick via the process of beta conversion. It seems like just intuitively that beta should be applied to p, and the result should be p tick instead of vice versa. Why is it on the right side of the function and not the left?
Okay. Well, let me just maybe I just remembered that. So equals beta is like a single symbol. You guys got that? Yeah. So it's yeah. So,
Simplified, not equals the result of simplification.
yes. Yeah. It's not like a p equals beta applied to p. No, it's p beta equals p. So essentially, that just means that yeah, it eventually reduces to p. So essentially, this is like a specific. It's kind of more concrete way of describing the down arrow. The down arrow is kind of just says any evaluation, and you might have other crazy evaluation rules that aren't beta reduction. But in here, we're just specifically saying this conversion rule is based on beta reduction.
These reductions must ends up in some kind of normal form, right? You cannot
Yeah.
compare some radix which accept some arguments. You compare reductions inside the body.
I mean, so it will eventually simplify itself. It might simplify itself to a abstraction which still, lambda x or for all x, and still expect an argument, but it will be in a normal static form. It will be one of the values. Did I put in the values for this? Okay, it's missing values.
We can have lambda in
Yeah. It can be because lambda normal form just means that it's like an anonymous function. Lambda x to x is a normal form. It's just
you can compare it with beta reduction. Makes sense.
Oh, I see. So, but then you can't reduce it further. You're reducing it as far as you can, and then if you end up with a lambda, then you have no arguments, then you can't reduce it further. But I mean, comparing. Okay, so that's a good question. And we can't, in a general case, compare two functions because that's undecidable. So this kind of brings us to the question: what does it mean to kind of compare things per equality? Because we could compare it tactically. We could just say, are they exactly the same? Maybe they are, but often they're not. Or maybe the names are different, and then we say we compare them modulo alpha equivalence. But in the general sense, so in the general sense, what happens here, since we're doing it at the type level, we can't compare, so imagine you have a function int to int, a very simple function. So you can, because you're comparing types, you're not comparing the function outputs or function extensionality, you're just comparing that the p and p dash are int to int, right? And in this case, they're equal. So I don't know if you ever heard that kind of notion that from a logical standpoint, all functions, int to int are the same, or bubble sort is the same as quicksort. So this is kind of that notion, is that in here we're using intentional equality, which just means that, yeah, we're going to compare their type signature. If the type signature is the same, for the purposes of the type checker, they're the same type. And maybe the implementations of those functions are vastly different.
So you're saying that there is only conversion for types, not for values?
Yes, so we have E of type P, and we do beta reduction on P. We're not doing anything with E. So in this case, you can try out variations, and you can. So Edward Kmet is working on extensional function equality, or extensional notion of equality. Those are rather trickier. Extensional in this context would mean that so intentional, it kind of like it compares the meaning, and the meaning is given by the type. Extensional is like the set theory version, is you're comparing the kind of like the output in a way, not the structure even. So for example, one set theory example is imagine the set of people in this room who have green hair, and the set of people in this room who have 3 legs. They're the same set of people because they're both empty. But from a type theory perspective, I've just said nonsense, right? Or from most perspectives. Extensionally, they're equal. Intentionally, they mean vastly different things.
So you compare the type of the set builder versus the output set?
Yes, yeah.
How do we treat polymorphism in respect to intentional equality? So this function from A to A can be equal to function from int to int. So, or in other words, can we treat a function of int to int as intentionally equal to A function? Because A to A function polymorphically can be an int to int function in some cases. Are they equal or not?
Well, they would be, as let's say, if you have a function, so explicitly A to A would be for all A dot, for all A of type, we have dot, I guess, we have it already. That's the more explicit way of describing the identity function. So if you do application here, and you apply it to int, then how is it going to beta reduce? Int comes here, so int of type, and then y is of type int, and the output is int. So, and that is the same as int to int. So what you said, so it's not that polymorphic functions are the same as int to int, but if you take a polymorphic function and you apply type int, then that is intentionally equivalent to the int to int function, because that's what it reduces to. It's a good question. Otherwise, if you don't do that, if you just keep your example, then what's going to happen? You have a function of ID of type x type to y type x to x. And what's it going to reduce to without the argument? That's a trick question.
Well, I guess it's not.
Yeah, it's not reducing, it's just going to stay itself. And then the question intentionally is this function the same as int to int? It's not. So, yeah. Yeah.
There is not, or you cannot say nothing, which is different. Because you're assuming that there is not the same. But yes, it's not the same, it's not equivalent.
Well, under this definition, I guess.
But you are not applying anything to say that there is no.
I see what you're saying, but so intentionally, even if you kind of this is a vastly bigger function than the function int to int. So even intuitively, you can imagine you can do much more. A function which takes in a type and then does something. You would. I guess you could, if you wanted to check that, then I guess you could just go the classical way and try and prove an isomorphism between them, and then.
Yeah,
Yeah. Yeah, but then again, there's more sense. That would be extensional. You prove that they're extensionally not equal because you prove that there is a value of one type that you can't. So to prove isomorphism, you have two types, and you need to convert every value to the other one, and then show that you can convert it back, and vice versa. So type B embeds type A, and then type A embeds type B in each other. And so yeah, I guess if you did that with type in, then yes, you'd prove it, but I don't think they're isomorphic. But yeah, so this is exactly the kind of questions type theorists or logicians ask. Is that they say that what does it mean that things are equal? Like when are they equal? So kind of homotopy type theory that aims to extend our notion of what it means for things to be equal. And then that means we can extend what type checks, because we can compare more things, and yeah, and then yes, syntactical equality of functions, yeah, that's like no one does that for the reason that it's just too unlikely that you're going to have two different functions match syntaxes. Like there's no way to pattern match not sensibly. But there's no way to, so in principle, yeah, we'd like to have this kind of extensional equality because because then we could separate. We have lots of functions int to int, and in this view of the world, we think they're all the same. It would be nice to separate them and say, actually, this is one that like addition is different to multiplication. But there's no way to automatically kind of do this extensional equality because that's undecidable. And if you could do that, you'd have you solve the Holding problem, etc. So inside, you could kind of imagine. And I don't know if you guys heard of like New Perl, and so in there they work with extensional equality. And I haven't used it myself, so I just know about it from a few presentations. But essentially, there you can have these explicit proofs that two things are extensionally equal, and then you are able to use that somewhere. So instead of just having this one rule, you have, like you said, yeah, if I give you the proof that A equals B, you have some ways to use them. Like maybe you convert between them in your junior type inference. You'll have some extra rules capturing that and then using them to infer things better.
What's the name of the tool?
I'll write down. NU Perl. I think the new version is called Red Perl. It's made by John Sterling from Carnegie Mellon, or wait, there's another university. Cornell, also Cornell. I think they're one of the original developers. So that one's very interesting, and there's an OPLSS talk on this by Rob Harper last year. So yeah, if you look at 2018 Oregon Programming Language Summer School, yeah, you'll see Rob Harper talking about it. It's a very interesting concept. But normally in like all of our Martin-Love type theory based languages, they come from the notion of intentional equality. It's like the standard. Good questions though, like that. Anything else is kind of like interesting there? I think we're kind of close to finishing, so there's no time to like. We're going to leave the implementation for tomorrow, but I'm happy to kind of answer anything else, even if it's like tangentially related.
So how does this whole extensional versus intentional dilemma relate to HOTT?
Okay, good question. So sorry, I think the main version of HOTT is intentional, but I think okay. So so homotopy type theory. Who's familiar with it? Yes. Who's implemented a homotopy type checker? Okay. So let me. I'm not an expert on this, but I can give you some intuition, perhaps. let's see. So there was this guy Vladimir Voyevodsky, and he had some radical ideas for doing type theory differently, and he wanted to. So he had this like very interesting definition of equality, which is I don't think I can reproduce it now. But essentially, it kind of related several different notions of equality. And if that, so he kind of postulated as an axiom initially, and then using this as an axiom was unsatisfactory for type theorists, because type theory were computing things. We can't just say X is true if we can't use it in a computation. So if this was anyone else doing it, then people would just ignore him. But Vladimir Voyevodsky was a Fields Medalist winner. And so type theorists said, okay, this sounds crazy, but maybe it has a point. And so there's this big question of what does it mean to implement this notion of equality, because if we implement it, we know that we're going to get some really cool equality properties out of it. Essentially that you have your, let me just try and say it very informally. Suppose you have a notion of equality which is very, very hard to get, such as the extensionality we described. But if you have it, then you can do loads of stuff with it. And he proved that this hard-to-get notion of equality corresponds or can be gotten from some simpler version of equality. So you kind of like by proving something that we would have thought was weaker, we're actually proving something stronger, and then we can use that. And in the case of homotopy theory, the probable ideas are that you could, for example, in some hypothetical future, we could vastly remove boilerplate from a code, because if we prove that some two things which are really, really weird looking and don't seem like have anything in common, but we prove they are equal in some mathematical sense, and then suddenly we can interchange them. And but so the notion of homotopy, where does the homotopy part come from, is that in order to kind of do all this reasoning, he formalized. So whenever you're defining a type, you're also defining like some notion of equality during your definition. So in addition to just having your, if you have your, imagine your general algebraic data type syntax and you're defining your constructors, in addition to your constructors, you're also going to define some notion of equality there. And the theory of how to do so comes from homotopy, where you treat your types as spaces, and then it's kind of like you have this whole, what does it mean to change one space into another? Yeah, it's relatively informal, but does that make any sense? Or if it doesn't, when does it not make sense? Let's see, it would be an interesting thing to build as well. So there's been a lot of research on homotopy type theory, so there are implementations of it. And so, okay, so here's one. So Rob Harper, who is at a Carnegie Mellon and CMU, but he's part of the people who's working on this new plural idea. He has a very different approach to formalizing homotopy type theory than the other community of type theorists, because normally people attempt to approach it using notions of intentionality, but he has in his talk that I mentioned, he explains how their extensional type system can like offer new insights into these implementations. So if you're interested in that, I think that's a good place to start, and new Perl or red Perl.
Regarding implementations of HOTT, I'm aware of cubical code and cubical lambda.
Mm-hmm. Yeah, I guess that's yeah, those are actually existing implementations. Also good to look into.
Can you compare? So Bob Harper was talking about this whole trinity between type theory, proof theory, category theory. So,
Yeah.
Can you say something about proof theory side, for example, like deep inference?
Okay, deep inference is not something I'm very familiar with. Just read bits about it. But essentially, okay.
They have notion of comparing proofs, right?
Yeah.
So in that sense, is this related to comparing beta reductions?
Okay.
If we compare the steps of reductions, then we can compare really, are they?
So it would go back to this question of what kind of equality are we using. And then you could approach this papers on deep inference, and then you can look at it and say, when they say that two proofs are equal, what do they mean? Like, how do they check it? And maybe it's by finding normal forms of the proof and by simplifying it, in which case it would be intentional, or maybe they using some other form of equality, which is also possible.
They're talking about comparing exactly the steps of reductions.
Ooh, okay, interesting. Steps of reductions.
Type inference is undecidable under this type system, right? So is deep inference, because I never heard this term, is deep inference something
I'm not sure, so that's why I asked.
okay. Because I never heard the term deep inference, to be honest. What I know is that type inference for this kind of type system is undecidable. You just can't in general answer whether the program, what are the types of the program without being explicitly given types.
Undecidable in the sense that
You cannot have an algorithm that will work for any program without explicit type annotations to determine the types. There will be some examples where type inference, where your algorithm will fail, basically, like a halting program. In that term, undecidable. So is deep inference something that changes that, or is?
Oh, you couldn't. Oh.
Oh, okay.
Yeah, it's a way of structuring your sequence, as far as I understand. So, does that make sense? So you have your. It's essentially. I mean, again, I've only like glanced at it briefly, but you have your. There's certain things you can do. Okay, cool. Yeah, certain things you can do with your sequence normally, and then deep inference allows some kind of obscure manipulations.
Class of type systems where inference is generally possible broader or not?
You can do, well, I mean, it depends on your broader inference. You know, we can add more type rules to this, and it's going to be broader inference, but it's not going to be a deep inference system. I think it's more of a.
I guess what I was asking is because when you go back to lambda Q, and then when you go from a simply type lambda calculus to system F, then somewhere in between there is a Hindley-Milner type system, which is the upper bound of inferable type systems. You can have a program, any program under Hindley-Milner type system with no type annotation whatsoever, and it can be deduced what the types are. Now, by saying broader, I mean whether this, and it's been proven that when you go up from Hindley-Milner, all these properties are lost, right? So this type system is an upper bound of inferable type systems under this definition. So my question is whether this deep inference changes this scale, whether it moves this point.
Well, I'm sure how
somewhere.
That does give a different upper bound, right?
Yeah, that's my question.
Yeah.
Whether it makes the range of type systems that are inferable broader.
Yeah,
Or
for
different,
efficiency.
right?
Or different.
Yeah.
Is that
My opinion
deep
is
inference is about
And also, just to expand on that notion, when the question of whether this type system is decidable, like, I guess it's relevant for everyone. So, strictly speaking, no, yeah, it's not decidable in the general sense. But in practice, the only times it becomes relevant is when you have some really, really, really obscure edge cases, and you're probably trying to do it intentionally, like the Girard's paradox, or the stuff I mentioned where you were able to prove that false is true. Yeah, if you're trying to encode these kind of weird things, then essentially the way you prove that false is true is that you create a computation which doesn't terminate. And you can do this on the type level. So you're going to try and you have a type checking imputation, and your type is so weird that it just keeps expanding forever. But in practice, as a programmer, this is highly, highly, highly unlikely you're going to bump into that. If you're a logician, you're trying to break these systems, then that's, yeah, you can find a few examples. So basically what I'm saying is that even though people describe it as undecidable, it's not really something which becomes an issue. And but it's also possible that, yeah, if let's say if we had a more naive implementation, then it's possible that, yes, we would have run into these issues more likely. So this is where the whole notion of designing your system well and having, for example, syntax-directed rules comes into play. Is that in our case, with our bidirectional type inference, it's very, very tight. Very few formation rules. Very hard. But once semantically. Sorry?
Is it a syntax-directed inference or semantic-directed? That's a syntax-directed.
Yeah, this is syntax, yeah.
That's a syntax-directed inference.
Oh, yeah, sorry, yeah, so, yeah. So it's not really, a question of whether, so it's not a question of whether it's syntax versus semantics, but it's a question of, is it syntax-driven or is it not driven? So,
So you said, I think you switched words. You meant semantically driven, because what we have is syntax.
no. So what, so it is syntactically driven, yeah, and that's what we try to design it as from the start, because for a computer, for a type checker, it doesn't have the notion of semantics. All it sees is the syntax. So what we need to do is, in our case, is that it's able at every point to pattern match it and say, this is the case I'm working with. And that's what kind of, as opposed to if you just look at some math presentation which doesn't try and make this implementable, then, for example, they might remove this distinction between the two. And then, so what happens then, technically, it would be correct mathematically. It would be true to say that in the one judgment way, it would just describe a mathematical relation. And the mathematical relation would still be true. But if you look at it, you say, how do I implement this? And it would not give you any directions to do so. It's just like, yeah, this is a mathematical relation. So the reason we're using the down arrows and up arrows is because we want it to be guiding an implementation. We want it to be amendable to an algorithmic proof rather than just an abstract definition of some abstract mathematical object which just exists in Pottering sense.